Okay, now we're going to do chapter 10, section 4, and it's the last section in chapter 10, and there's quite a bit going on in it. Excuse me. Okay, so we have measures of central tendency. Two important aspects of data are its center and its spread. So let me preface this with in the last two sections. Okay, in the first one, remember, we just talked about statistics and gathering the data, and then we looked at in the next two sections displaying the data. So now we're going to kind of look at analyzing the data. So two important aspects of the data are its center and its spread. The mean and the median are measures of central tendency that describe where the data are centered. The range, the interquartile range, the variance, the mean absolute deviation, and the standard deviation describe the spread of the data and should be used with measures of central tendency. So we're interested in kind of where the data is centered and how spread out the data is. So first of all, the number commonly used to characterize a set of data is the arithmetic mean. This is frequently called the average or just the mean. Technically, we've got three terms here that could be called the average. The mean, the median, and the mode are all types of an average. And so if you are looking at a report or some data, and it just says the average is, you should be suspect of it, right? Official statistical reports should either tell you the mean is such and such, the median is such and such, versus the mode. That's hardly ever used, and we'll see now, but it is technically an average. So the mean of the numbers, if we had x sub 1, x sub 2, denoted x bar, right? So this is what we're going to call the mean. It's x with a bar over it, and it's red x bar. I tried to correct this slide, but it wouldn't let me. This KKK right there is supposed to be dot, 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 right? So to find the mean, and this is what we typically think of when we use the word average, just the common lay person, is you add them all up, and then you just divide by how many there are. Okay, the mean is actually a balance point. So if we think of the mean as a fulcrum, like a balance beam, and we have a bar going across there, and we can see that even though there are 4 values over here and 2 over here, it would balance about the mean. Because look at what this is. The 4 is 1 unit away from 5. Whoops. Pen. The 4 is 1 unit away from 5. And then there's a 3, so now you've got something that's 2 units away. There's another 3. And then there's a 2, which is 3 units away from 5. If we add that up, 3, 5, 7, 8. On this side, the 8 is 3 units away from 5, and the 10 is 5 units away from 5. If we add those distances up, notice we get 8 on both of them. So that's what we mean by the balance point. Okay, if you placed weights at these positions, it would balance right here at the mean. The median, on the other hand, is the value in the middle of a set of data. So you're going to have the exact same number of data points on either side of the median. The mean, you don't have the same number of points on either side, but you have the sum of their distances from that point is the same. If you're going to find the median, you arrange the numbers in order from least to greatest. Technically, it could be greatest to least, but anyhow, put them in order. Okay? If n is odd, then the median is the middle number. If n is even, you find halfway in between those two middle numbers. In other words, find the mean of those two middle numbers. Come on, come on. There. Sorry, guys. Okay, and then the mode. So we had the mean, we had the median, now the mode. The mode of a set of data is sometimes reported as a measure of central tendency, but that's wrong. It's not a measure of central tendency, but it is an average, right? It's one of the averages. I don't know that anyone ever reports it as a measure of central tendency, but if they do, that's a misused term. So it's the number that appears most often, okay, if there is one. But the mode does not have to be in any way a measure of central tendency. Okay, the high score could be your mode. A mode is frequently reported with categorical data. So let's see if, we're going to find the mean, the median, and the mode for this set of data. All right, so if we wanted to find the mean, remember we can represent that as x bar. To find the mean, you simply add up all your data points. This is the typical thing we think of when we think of the word average. What most people mean by the word average is actually the mean. Add them all up, 1, 2, 3, 4, 5, 6, and divide by how many there are. So let me get to my calculator, and we have 60 plus 60 plus 60, 17. So 540 divided by 6, or 90, is the mean. The median, we put them in order, and I notice they're already in order. And I could do this thing where I just count from both ends, and come and realize this is exactly in the middle. I'm going to change colors with that just to help us keep them different. Right, in the middle. So now I know I need to get halfway in between 70 and 95. Notice from this point right here, there's 3 numbers on this side, 3 numbers on that side. So halfway would be 70 plus 95 over 2, or I don't know what that is, or 165 over 2, and what's that, 82 and a half? Okay, just check my math here. Yeah, 82 and a half for the median. Now keep in mind, that's sufficient for a small set of data, but what if you had 45 pieces or something? It's unmanageable to find which number is in the middle. So I also have this formula that I want to remember. M plus 1 over 2. Right? I want to keep up with that. Where n is the number of data items. So in this case, 1, 2, 3, 4, 5, 6. So 6 plus 1, 7 over 2. And what that tells me, now be careful, a lot of times people think, oh, that's telling me the median, but it's telling me the position of the median. Okay, so this means, oh, 3.5, I need the number that's halfway between the third and the fourth data item. Okay, to find the mode is the number that occurs most often. So if I'm looking at these, I notice that I have two values of 60. So the mode is 60. Just the one that occurs most often. Oh, I also noticed I was about to add a data point, but good, they had a good example here. And 95. You can have more than one mode. If you have two modes, you will call that data set bimodal. Okay, and it depends on kind of the text you go with. Sometimes they'll allow 3 modes, but technically, in my personal opinion, I think once you get more than 3 modes, then we're going to say you don't have a mode, because you do not have a value occurring more often than any of the others, right? Let's say this had been 100. So if you had a 60, 100, 195, you don't have anything occurring more often than the others. But you can have 2 modes, okay? The mode is just the one that occurs most often. You'd think my little thing would have a erase everything, but I couldn't find one. Okay. All right. So the mean, the median, the mode. I really don't expect that to be new for any of you. Hopefully. Okay, choosing the most appropriate measure of central tendency. Although the mean is the most commonly used average, right, average in quotes, to describe a set of data, it might not always be the most appropriate choice. So suppose a company employs 20 people. The president of the company earns $200,000, the vice president earns $75,000, and there's 18 part-time people earning $10,000 each. Is the mean the best number to choose? So if we've got 8, so I'm going to add all those up to find the mean. Good grief. And if we have 18 people earning $10,000 each, then I would add $10,000 18 times, right? And then I'm going to add $75,000 and $200,000. And then I'm going to divide by how many there are. Now remember, there's 18 10,000. So 18, 19, 20. All right, let's see what this is. All right, 455,000 divided by 20. So that is 22,750. So is that really an appropriate average for these salaries? 18 of the 20 people in this place make $10,000. Saying that the average salary is 22,000 isn't really appropriate. Notice if we had this spread out, we would have 18 10,000s, right? So let's just say we had 10,000, and we had 18 of them, that's 100,000. Okay, if we had 18 of them, and then we had a 75,000 and a 200,000, the median is going to be 10,000. Even if I added another value over here or over here, right, it's still going to be 10,000, which is more representative of what an average salary for this company would be. Anytime you're talking about salaries, that's one of the things you should always be talking about the median. So that's something too. The mean is affected by these outliers, right? It pulls your average, your center, towards this direction. Okay, the median is not really affected by extreme values. Okay, for example, let's take this company. Let's say, the workers find out that there's another plant in the next town doing the exact same thing, but their average salary is $20,000. And they go to the boss and they say, look, our average salary is $10,000 and they make $20,000 as an average. I think we need a raise. So the boss could go and calculate the mean and come back and say, look, our average salary is $22,750. You're already making more on average than the other guy. Okay, so just throwing that word average around for everything isn't really good statistical methodology. So keep that in mind. We want to know what average we're talking about and what's the appropriate average to use for particular situations. Okay, here's one that's asking, is the median the best average? So let's look at the median. Okay, they're already in order. 1, 2, now this is a small group, so I could just kind of count from both directions with my fingers and find the one that's in the middle, but just to practice how I'm always going to find the median, just so we'll remember this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So remember that formula. So that would be 9 plus 1. Oh, the fifth number, when it's in order, is my median. 1, 2, 3, 4, 5. So 92 is the median. Okay, does that seem to represent let's say, oh, this person's average, on his test are 92. That's not really representative of how much this student knows, is it? I mean, at half the class, he was failing on half the information. So saying he had an average of 92 indicates that he's successful in everything in the class. This is why for grade averages we typically use the mean, so that these values down here carry some weight. Okay, is the mode an appropriate average for the following test scores? Okay, 40, 42, 50, 62, 63. The mode is 98, the only one that occurs most often. And for the most part, not 100% of the time, but for the most part, if you're asked this question, it's nearly always going to be no. Okay, I mean, maybe if you're talking about the color of people's cars, and there were 20 people driving a red car, and 5 that had a black one and 7, then you might use the mode, right? But for the vast majority of times, mode is really just not an appropriate average. Okay, although it is, a type of average, not a measure of a central tendency. Here's an example of why it's not a measure of the central tendency. This data set is nowhere centered around 98, but is a kind of average. Okay, so those are our measures of central tendencies. Now we're going to move and start talking about measures of spread. And they just kind of jump right in here with a slide without explaining what we're about to talk about. But we're about to talk about something called the interquartile range. We'll see that written in just a minute, or IQR for short. So I think there's 2 or 3 slides here that need a little explanation. So one measure of spread that we have, oh no, I moved my thing, it popped to the other side. I gotta move it back. Okay. Is the range. And all the range is, it's just the highest value minus the lowest value. So for this data, you know, because it's already in order, right? You find the highest value, you subtract the lowest value, that's your range. The range of this data is 15. Okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 11 divided by 2 is 5.5. That means I need halfway between the 5th and 6th value, right here, to find the median. So halfway in between 26 and 27 is 26.5. Okay. All right, so we've got the range. And then the reason they found the median here is they want to talk about the interquartile range. Okay, so coming up. Okay, they found the median to be right here. Right? So if you take your data and you split it in two, then you find the median of each half. Now, had there been a data point in the middle here, when I split it in two, I don't count that. So I would just mark out that middle point, that median value. Okay, if the median falls in between two numbers, I don't have to worry about it. And then on the first half, I find the median again. So right here is the median for this half. And on the second half, I find the median. And then if I subtract these two numbers, this is where the 28 minus 22 is. That's called the interquartile range, right? And so here it is, interquartile range, or IQR. Okay, we're going to talk a lot about the interquartile range, and actually these 5 numbers, your lowest one, this, which we're going to call the first quartile, this, which is the median, or you could call it the second quartile, and then this number is the third quartile, and then that's the upper limit, right? Those 5 numbers, the lowest, first quartile, median, second quartile, highest. Okay, that breaks our data into 4 evenly spaced sections, right? Those 5 numbers. Which means this part, what they're saying right here, is the interquartile range tells us where the middle half of the data is, right? That's what that is. That's the interquartile range. All right, so that's one measure of spread. We could just do the range, you know, the highest from the lowest, or I could find this middle half, how spread out the middle half is, the interquartile range. And I could draw a box plot with that. So here's another display option, okay, to add to our list of charts and graphs we've already done, is making a box plot or a box and whisker plot. Okay, they show the visual representations of the 5 number summary that we were just talking about. Okay, and we can make a lot of conclusions by looking at a box plot. So let's see if we can construct one. Well, we'll construct one after they've shown us. All right, so here's a box plot. Here's what it looks like. This is why it's called a box and whiskers, right? Your lowest value gets a point. Notice there's 5 points here. They correspond to that 5 number summary. So here's the lowest value. This is the first quartile, the median or second quartile, third quartile, highest value. Okay, you draw a box around these 3 middle ones and then whiskers going to the end ones. Okay, so this is asking what are the minimum, maximum, the median, and the lower and upper quartiles. Okay, so the minimum value is 0. the maximum value is 70 for this set of data. Okay, the median is 20. The lower quartile, you can call the first quartile the lower quartile, it's 10. And the upper quartile or the third quartile, either one, is 35. Okay, but this, a box and whiskers plot, tells me all kinds of stuff about my data. For example, I know that half of this data falls in between 10 and 35, right? That's half of the data. I also know that another half of the data is from 0 to 20. The lower half is from 0 to 20. The upper half of the data is from 20 to 70. I can tell, oh, it's a lot more spread out, that top half of the data, than this lower half, right? The middle half goes between 20 and 35. Not only that, this is a fourth of the data between 0 and 10, a fourth of it between 10 and 20, right? A fourth, a fourth, a fourth, a fourth. Because remember, these 5-number summary went exactly halfway and then halfway in between those two halves. So there's the same number of points, not a balance, not the same value, but the same number of points in each of these sections. Okay, an outlier. Now remember we talked about outliers before and we said we'll discuss them in more detail later. So an outlier is a value that's widely separated from the rest of a group of data. So for example, look at this set of scores. 91, 92, 92, 93, 93, 93, 94. All of these are grouped close together, and so no values are widely separated. But look at this group of scores. 21, and then it jumps all the way into the 90s, and then it jumps into 150. So we can see that 21 and 150 are widely separated from the rest of the data. They're potential outlier. They may not actually be far enough away to be an outlier, but they're potentially an outlier. If we would have seen these values on our dot plot earlier, we'd call them outliers, right? But now we're going to see, well, how do we know if they are indeed an outlier or not? An outlier is any value that's more than 1.5 times the interquartile range, either above the third quartile or below the first quartile. Okay, we'll indicate them with an asterisk, and then we only draw our whiskers to the points that are not outliers and mark them with an asterisk. The reason for that is if they're so far away like that 150, say those were test scores, and I see a 150 and I'm thinking, I don't really believe that data value. So depending on what our data is, it might represent, hey, that was probably an error. Maybe just, it was a typo, somebody misread however they were gathering the data. So outliers are potential problems, and they could just be discounted, right, from whatever calculation you're doing. All right, so it says the table shows the final medal standings for the top 20 countries in the Summer Olympics. Draw a box plot of the data and identify possible outliers. Okay, so here's our numbers. They made note of the lowest score and the highest score, right? Found the median. They put them all in order. Found the median, and we're going to actually construct a box plot in a minute, so don't worry about that. And then they found the first quartile, the third quartile, and they found the interquartile range, which technically, to just construct the box plot, if there are no outliers, I don't really need to calculate that. That's not part of my 5-number summary. If you're asked for the 5-number summary, it's these 5 values, the lower, upper, and then, your 3 quartiles. Okay, so outliers are, but if you've got a suspect score, you calculate the interquartile range, and then you take the upper quartile and you add 1.5 times your IQR, So apparently you would get 83.25. Any number above 83.25 is an outlier. Notice 100 and 110 were both outliers. Any number above this point right here, right, would be considered an outlier. And then you do the same thing for the first quartile, but you subtract 1.5 times that. So to be an outlier in this direction, you'd have to have negative 22.75. So my low score of 11 is not really an outlier there. Okay, comparing sets of data. Box plots are used primarily for large sets of data or for comparing several distributions, right? It's really nice for comparison. So the stem and leaf is usually a much clearer display, but remember, it's only useful for smaller data sets. So if I have quite a large data set, I might prefer this box plot. Parallel box plots drawn using the same number line. That's going to be important, the same number line. Give us the easiest comparison of medians, extreme scores, and quartiles. Although we cannot spot clusters or gaps in box plots, like we can with stem and leaves or line plots, we can still more easily compare data from different sets. Also remember, the line plot is for small data sets, right? With box plots, we do not need to have sets of data that are approximately the same size even, like you kind of do even with a double stem and leaf. Okay. To compare data from two or more sets using their box plots, first study the boxes to see if they're located in approximately the same place. Consider the lengths of the boxes to see if the variability of the data is about the same. And check whether the median, the quartiles, and the extreme values in one set or another are greater. So here's an example. Okay, two box plots. Earnings by gender. We've got male earnings, we've got female earnings, right? We should notice a lot of things right away. Let's see what they say. From the box plot, we can see that the mean salaries for males have been higher than those for females. Okay? Since the extreme values, the median and the quartiles are greater. So notice every one of those are greater. Here's the extreme low end. Even the male's lowest end is higher than the female's. The highest end way higher. The median value higher. Each quartile higher. Right? More than 50% of the mean salaries for males are greater than those for the mean salaries for females over the time period. Well, I don't know about more than 50, because here's what we know, right? This is 50% of the male salaries, right? Well, okay, so I guess what they're saying is this 50% is higher than this 50%, but that's not a fair comparison. You want to compare the same. The upper 50% of the male salary, nearly all of it's higher than the upper 50% of the female salary, but not all of it. You can't make that definitively because it looks like this goes a little higher than their half, right? And even the same thing here. I can't say this middle 50% is all higher than the female's middle 50%. But still, we can get a good comparison of how much higher male salaries are than females. Okay, now we have variation. Right? How much the data is varying from the center, how much dispersed it is. So it's another kind of dispersion. The variation, the mean absolute deviation, the variance, and the standard deviation. Now we're mainly going to be interested in standard deviation, but you might see in elementary school mean absolute deviation, junior high I guess. But typically the standard deviation is a better measure of that. So a measure of spread is needed when data are summarized with a single number, such as the mean or median. The simplest way is to find the range. Okay, we talked about what the range is. It's the highest minus the lowest. That's the simplest way. but that's not really a good measure of the spread. Think about if your data scores were 0, 75, 76, 77, 78, 80, 82. Okay, if you did 82 minus 0, you're going to say, oh, that spread is 82. It's going to look like, whoa, that data is all spread out. And it's really not. It's just, it had an outlier, right? So the range, not really a reliable source of the spread. We can also use the interquartile range. Okay, so we've got that. But the most sophisticated, they're going to call it, is the standard deviation. Okay, so they say that, and then they jump back and talk about the mean absolute deviation. But okay, they're very, very close. So the mean absolute deviation makes use of the absolute value to find the distance each data point is away from the mean. So the standard deviation and the mean absolute deviation are really the same type of measure. What you're doing is finding, on average, how far every point, every single data point is, on average, away from the mean, right? The only thing is this makes use of absolute values, and the standard deviation makes use of squaring, and we'll see why in just a minute. Okay, then the mean of those distances is found to give an average distance from the mean for each of the points. Okay, now here's the instructions where it tells you to find the mean absolute deviation. Since we're going to actually do the steps, but you can, pause this and have it if you want to make a list and some notes, that's fine. Okay, this is a formula for it. Also, this right here, it should be dot, dot, dot. I don't know why every time they do a dot, 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 it's turning into a K, and it wouldn't let me correct it. They've used some kind of a math type that isn't compatible with my computer. But anyhow, I don't really need this. As a matter of fact, I nearly even deleted this slide, but if you see it, it's going to be the same for the standard deviation. I don't really need that formula. Okay, what we're going to do to calculate either one is make a table, right? So here's what you do. First, you list all of your scores, right? All of your data points. This one happens to be test scores. Then you find the mean. Okay. Then I'm going to subtract the mean from every single data point and take the absolute value. The reason that we do that is if I subtract this mean from this data point, notice this is going to be a positive number, a positive number, a positive number. Then I've got a negative and a negative. When we actually do this, I'll show you. But if I added this up right now, I would get a 0 every single time. Because remember, that's what it means to be the mean. The mean is your balance point between that data. So if you're trying to find the distance on one side for every data point and the distance on the other, and take their difference, it's 0 every single time. So the mean absolute deviation takes the absolute value of each number to get rid of the negatives. Standard absolute deviation takes the square of this number to get rid of the negative. Okay, that's the only thing. So then you add them up, divide by how many values there are. In other words, take that average, and that's your mean absolute deviation. All right, the variance and the standard deviation are two commonly used statements of dispersion, way more common than the mean absolute deviation. These measures are also based on how far the scores are from the mean, except instead of using absolute value, it's going to use squaring. Okay, so once again, here's the steps. If you want to pause this and make yourself a list of the steps, but we're going to actually perform these steps. So I'm going to go on. And there's the formula for the standard deviation, which we don't really need to know. But in case you see it, again, that should be dot, dot, dot. Okay, here we go. Professor Abel gave 2 group exams. Okay, exam A had these grades, and exam B had these grades. Find the following for each exam. Okay, the mean. Okay, pin. Okay, so the mean. I'll call it this for group A, right? The mean for A. I'm going to add them all up. 1, 2, 300. Add them up. Divide by 1, 2, 3, 4, 5, 6. Divide by 6. So the mean for A is 50. Okay. For B, if I add them all up, 1, 2, 3, 4, 5, 6 50s, that's 300. And there's 6 of them. So that's 50. Notice here's the point they want to make with this, why they gave such oddball data. But your mean could be the same. And so we need more information because look how different these two sets of data are. But if we just looked at, their mean or their average, we'd get the same number. Okay, so the range, since I'm red, I'm going to do B first. The range is simply the highest minus the lowest. So 50 minus 50, in this case, is 0. And then for A, I'd have 100 minus 0, or 100. So notice that tells me a little bit, in addition to the mean. Okay, they're centered in the same place, but if I only look at the range, if it's not real important scientific, study, then this would be a good enough one. Oh yeah, these are spread out a whole lot more, and these are not spread out, which tells me about the data. Okay, the mean absolute deviation. Here we go. To find the mean absolute deviation, I'm going to make a chart, right, where I'm going to put the test scores here. So I'm doing A first. 0, 0, 0, 100, 100. 0, 0, 0, 100, 100, 100. Okay, and over here, I take every one of these scores and I subtract the mean from it. 0 minus 50, 0 minus 50, 0 minus 50, 0 minus 100, 0 minus 100, 0 minus 100. So, no, that's not what we have, is it? Sorry. Okay. 100 minus 50, right? Take the data point. Sorry, I hope that didn't mess you guys up too bad. Take the data point and subtract the mean. So here's my data point now. All right, so I get negative 50, negative 50, negative 50. Notice now I get positive 50, positive 50, positive 50. If I were to add this up right now and try to take the average, this is how far every point is away from the mean. But if I try to take that average, I've got negative 150, it'll be 0 every single time because of what it means to be the mean. So this is why on the mean absolute deviation, now they're going to take the absolute value of every one of these, right? The absolute. So that reminds me, oh, this is the one where I'm taking the absolute value. So the absolute value of negative 50 is positive 50. The absolute value of positive 50 is also positive 50. Okay, so now when I add these up, 5, 10, 15, 20, 25, 30. Yeah. And then if I divide by how many there are, 50. Let's do it for the other data set. Okay. This time I have 50. 1, 2, 3, 4, 5, 6. Okay. I'm going to subtract the mean. I forgot to write my heading over here just so that we would know what we're doing. Okay. The mean is 50. So I have 50 minus 50. 50 minus 50. All the way down. Okay. Notice, once again, if I tried to add these up, I'd get 0, but that's because this one's going to be 0, right? Technically, now we would take the absolute value of all these, add them up, divide by how many there are. So notice the mean, and these are just wonky data sets, so the mean and the range on set B happen to be the same, and the mean and the mean absolute deviation and the mean happen to be the same on A, and the mean absolute deviation and the range happen to be the same on B. Okay, that's just because these are wonky data sets. But that's the process for finding the mean absolute deviation. All right, let's see. We're going to do a better example, I hope. I know they were trying to make a point with that data, but I should have changed it. But it's all right. All right, let's see what we've got now. Oh, and now it asked me to find the standard deviation. Okay, so the standard deviation and the mean absolute deviation is very much the same. I'm not going to do it where they're all 50, because again, that's going to be 0, right? But let's look at the little bit of difference in this data set. So we had 100, we had 100, we had 100, 0, 0, 0. I think that was our data. Okay, I'm still going to find the difference between each data point and the mean. So I still need to do this 100 minus 50, 100 minus 50, 100 minus 50, okay, 0 minus 50, 0 minus 50, 0 minus 50. And again, when I get these values, it's just like we talked about before. It's always going to give me a 0 over here, even when the deviation isn't 0. So in order to get rid of these positives and negatives, it's going to add to 0. The difference in the standard deviation and the mean absolute deviation is that instead of using absolute value to make it positive, we're going to square these values. All right, I'm going to square them. And I'm getting off of my thing, but we know there's 1, 2, 3, 4, 5, 6, right? All right, so 2,500 All right, now this is what I add up because it's no longer 0, right? So there's 50, 150. So 15,000. Okay, and now we're going to find basically that average. So I'm going to divide by 1, 2, 3. We know there's 6. 15,000 divided by 6 is 2,500. Duh, it's 2,500. Again, weird data set. Okay, at this point, what we have right here, this is called the variance. So you notice that was one of our terms. This is the variance. If I go back in and undo this square by taking the square root of this number, then that's the standard deviation. Okay, and once again, I know we got the same thing as the mean absolute deviation. It's because this is a stupid data set. Okay, I'd redo it, except I'm not going to redo this whole video. I think I put another one in there for us to do towards the end. This is their example. Okay, so the variance and the standard deviation. Then it asks us to find the median. Okay, so once again, if I'm finding the median, I put them in order. Least to greatest, greatest to least, it doesn't matter. Okay, I need the number that's in the middle. So since there's not an actual data value in the middle, halfway in between 100 and 0, the median for this data set is also 50. All right, if I'm going to find the interquartile range, right, I'm going to find my median. So I'm going to, the median is here. And then the median for this half and the median for this half, and I subtract those two. So the interquartile range is 100 minus 0, or 100. I didn't think this example through when I saw it. I thought, well, that's a stupid example and wonky, but I knew kind of what point they were trying to make there. But I didn't think it through that every single one was going to be silly, so sorry about that. Let's see if we can go on to something that's a little more meaningful. I know one of these has to completely clear the page, but whew. Okay, the normal distribution. So at the end, I think I've put in an example where we'll do that. If not, we will add one because I might not have. Anyhow, we'll do one at the end. Another standard deviation. Okay, the graphs of normal distributions are the bell-shaped curves called normal curves. A normal curve is a smooth, bell-shaped curve that depicts frequency values distributed symmetrically about the mean. In a normal distribution, the mean, the median, and the mode all have the same value. And tons of things are just naturally, normally distributed, right? Think about the weights of babies when they're born. And I don't know what the mean is, but let's say it's 7 pounds. Okay, that means that most of the babies weigh 7 pounds, It's also the middle number, and it's the mean. But there's just as many babies that are born that weigh 6 pounds as that weigh 8 pounds. There's just as many babies that are born that weighs 5 pounds that weighs 9 pounds, right? So anytime you have something with a large population, weights of babies at birth, heights of women versus heights of men, it's normally distributed. And so a lot of things are naturally normally distributed. And then other things, when you have giant populations, they become normally distributed. So in a normal distribution, the curve extends infinitely in both directions and gets closer and closer to the x-axis, but never actually reaches it. The curve is symmetrical about its center point, but not all symmetrical distributions are normal. Let's see, for example, I could have so here's what, and we're about to see a picture of this. That's what we're talking about, right? It's like a bell-shaped, and it's symmetrical about this point in the middle. But I could have another, it's symmetric, but it's not normally distributed. Okay, so here we are. Here's a picture of what a normal distribution looks like. Okay, now some of them may be flatter, some may be taller and skinnier, but they're all symmetric, all bell-shaped, and I need to memorize these numbers or make note of them, right? 68, 95, 99.8. Okay, typically that's 99.7. I guess they're trying to make your math a little bit easier, but I thought on this book, this new version, they actually put that 99.7. So pay attention on your homework, see if they're going to use 99.8 or 99.7 right there. Okay, so anytime a problem tells me something is normally distributed, and then it starts asking me questions, I'm going to draw this curve, and then I'm going to fill in these numbers. Okay. For example, when a standardized test was scored, there was a mean of 500 and a standard deviation of 100. Suppose that 10,000 students took the test and their scores had a bell-shaped distribution, making it possible to use a normal curve. Oh, if it tells me the distribution is anything near normal, then the first thing I'm going to do is I'm going to draw that curve. I thought I clicked black. All right, so I'm going to draw that, trying to make it fit on here. I'm going to draw a normal curve. I'm going to draw that bell. And I'm going to fill these values in. I'm going to try to make it symmetric. And I know that in between these two numbers is 68%. And then in between these two numbers is 95%. And then in between these two numbers is 99.7. Typically this one's saying 99.8. So pay attention to when you start doing your homework. I know this book historically has used 99.8, but I thought I saw it changed in this version. Okay, so no matter what numbers are, as soon as it says normal distribution, I draw this for every single one. Doesn't matter what we're talking about, what the mean or the standard, it doesn't matter about anything other than normal distribution. I draw this. The only thing that changes from one normal distribution to the other are the numbers. So now where these numbers come from, the mean goes right here in the middle. And the standard deviation, I'm going to add 3 times. So this one will be 600, 700, 800. And then I'm going to subtract 3 times. 400, 300, 200. Every single time it says anything about a normal distribution or being normally distributed, I draw this and then I put the mean in the middle, add the standard deviation 3 times, subtract the standard deviation 3 times. Now, I can answer all kinds of questions about it. This first one says how many scored between 400 and 600. Notice here is between 400 and 600, right? That coincides, to this number right here. 68% of the people scored between 400 and 600. If I know there's 10,000 students that took it, then 68% of, multiply, of 10,000, right, is 6,800. So 6,800 students scored between 400 and 600. That's what this is telling me. Okay, I think we're continuing questions with this, so I'm going to leave the same drawing. So, same question. Okay, how many scored between 300 and 700? All right, well, 300 and 700, that's this number to that number. Oh, look, these numbers coincide exactly with this 95%. So 95% of them did. Okay, so 95% of the 10,000 students, or 9,500, scored between 300 and 700. How many scored between 200 and 800? Well, look, there's my 200 and there's my 800. So 99.8% of those students did. All right. So this is the percentage. If I wanted to know how many, right, I've got to be, do the 0.998 times 10,000 to get that final answer. Okay, but what we want to look at, what about one like this bottom one? How many students scored above 800? Above 800. All right, well, that means this number. If from here to here is 99.8%, remember this whole thing all the way is 100%. So if this much is 99.8%, then the rest of my graph, meaning this and this, has to be 0.2%. Right? 0.2%. But it only asked me about the students above 800, not or less than 200, right? So half of 0.2% is 0.1%. So 0.1% of students scored more than 800, right? So 0.001 of your 10,000 students scored above 800. Okay, what if it asks us, how many students scored less than 400? Again, here's 400. So less than 400 is this group of students. Well, once again, pay attention to where your number falls. If this much is 68% and the entire graph is 100%, that means these other parts, the rest of this graph, besides right here, 68%. So this and this has to be 32% to make an entire 100% of the students. So if this part and that part together is 32%, because it's symmetrical, it's the same on both sides, this half over here is 16%. So 16% of the students, so 16%, so 0.16 times 10,000, 16% of 10,000 scored less than 400. So notice I could just, once I've drawn my normal distribution, which is the same for every single normal distribution, then I can answer all kinds of questions about it. Lots and lots of info in this one section, isn't there? All right, let's see what else we have. Oh, an application of the normal curve. This should be interesting for you guys. Suppose that a group of 200 students ask their teacher to grade on a curve, right? I always have students wanting to grade on the curve. They think it just means adding points to your grade. That's not what it means. It means making your scores fit into a normal curve. Okay, so notice they've drawn the bell curve. They found the mean and the standard deviation, 71. The standard deviation is 7. So if you add 7, you put 78. Add 7 again, you put 85. Add 7 again, you put 92. If you subtract 7, you get 64. If you subtract 7, you get 57. If you subtract 7, you get 50. Okay, that means that anyone making between a 64 and a 78 would get a C. Anyone making between a 78 and an 85 gets a B. Over an 85 is an A. Between 57 and 64, a D. So that's what it means to grade on the curve. It's kind of nice to know since we're going to be teachers, right? Percentiles. When students take a standardized test, such as the ACT or SAT, their scores are often reported in percentiles. A percentile shows a person's score relative to other scores. Okay? Percentiles divide the set of data into 100 equal parts. Deciles are points that divide a distribution into 10 equally spaced sections. And I don't think we're going to talk about deciles, but percentiles, you see that a lot in elementary school because a lot of their standardized tests are in percentiles. Okay, this also really just the notation we use, percentile, right, sub R. Okay, so what a percentile means, let's say someone scored in the 80th percentile. Okay, it didn't mean they made an 80 on the exam. They could have made a 20. Yeah, but it just means out of all the people taking the test, they scored higher than 80% of the people taking it. Okay, so that's what a percentile means. So Aussie was ranked 25th in a class of 250. What was his percentile rank? Okay, so if he was 25th in a class of 250, the first thing I need to know is how many people scored lower than him, right? If he was ranked 25th, the 25th best one, that means 225 people scored lower than him. That's what a percentile tells us. So I'm going to take 225 out of the total number of people. Let's see. Oh, that's 0.9. 0.9 is the same thing as 90%. So he was in the 90th percentile. Means he scored higher than 90% of the people in his school. Okay, in a class of 50, Kathy has a percentile rank of 60. So what is her class standing? Okay, so since her percentile rank is 60, that means 60% of those 50 people, so of those 50 people, scored lower than Kathy. Okay, so you got to change that to a decimal. Of course, means multiply. 0.6 times 50 is 30. Right? Now, I got to remember that 30 is not her standing. She scored higher than 30 of the people, meaning her class rank is she was 20th in the class. Here's another use of percentiles. This is why college entrances and things look at your percentile ranking instead of your ranking in the class. Look, Aussie went to a giant school where he had a graduating class of 250. Okay, but look, it showed if you just look at their class ranking, his ranking is farther, is behind Kathy's. It says Kathy, oh, she's 20th in the class. Aussie's 25th in the class. But look at their percentile ranking, right? Aussie scored higher than 90% of all these students. That's a lot of students, higher than 225 students. Kathy just scored higher than 30 students. So there's a use of percentile ranking. Okay, so percentiles. Hopefully, I think that's the last topic, so I hope I put a slide in here for an example. Now that I'm thinking of when I made this PowerPoint, I'm thinking I went back and took away their working and just worked through that oddball one for them. So let me see. Yeah, that's the last slide. Okay, so that's the last slide. Let me do something here. Okay, so I feel like we need another example of a standard deviation that's not weird. So let's say we have these data values, 7, 5, 2, 3, 8. Okay, and I'm trying to find the standard deviation. The first thing I need to do to find the standard deviation is to find the mean. So I'm going to add this up. All right, so 12, 13, 14, 25. Hey, look at that. Whoops. 25 divided by 1, 2, 3, 4, 1, 2, 3, 4, 5. Cool. So my mean is 5. To find the standard deviation, I need to make myself a chart and list all my data values. They don't necessarily have to be in order, but I'm going to put them in order just for the fun of it. Okay, I'm going to subtract the mean from each one. And notice if I add here's kind of a double check. I always like to, just take a glance and see if this will add to 0. If it adds to 0, I feel comfortable I'm on the right path. If it doesn't, I've already made a mistake. That will always add to 0. Okay, and because of that, then I'm going to square each one. All right? So negative 3 squared is 9. Negative 2 squared is 4. 0 squared is 0. 2 squared is 4. 3 squared is 9. Okay? It doesn't always come out to be the exact numbers with a positive and negative, but many times it does, but not always. Then I'm going to add these together. Let's see, 13 and 13 is 26. Okay? And I'm going to kind of find that average. This is how far every point is away from, this is how far every point is away from the mean. So 26 divided by 1, 2, 3, 4, 5 gives me 6 divided by 5 is 5.2. That's my variance, right? That's my variance. Now, if I want to do the standard deviation, I'm going to undo this squaring that we did by taking the square root of 5.2. I'm going to round to 2 decimal places. Of course, it's non-ending. So 2.28 is my approximate standard deviation for this data set. Okay, so on average, every point is about 2.28 away from the mean. Okay, here was the mean, 5. Oh yeah, that's a little over 2 away, a little over 2 away, a little over 2. On average, that's how far spread out or dispersed your data is. Okay, a lot of information in this section, but it finishes up chapter 10, and then we'll go in now and do chapter 9. There's only 3 sections left. Let me know if you have any questions or need anything at all. If I don't erase that, it just stays on my computer screen forever. Okay, bye guys.